Hello friends, and welcome to our second video lecture on topic R3.2 electron transfer reactions. Today's lecture is all about electrochemistry. Our guiding question continues to be, what happens when electrons are transferred? These are our understandings. If you want to pause the video and read, they are all about these super cool electrochemical cells. And our objectives are first to define what even is an electrochemical cell, and then we're going to look at three different types. We're going to look at primary cells, secondary cells that are rechargeable, and then we'll wrap up with a look at electrolytic cells. Electrochemical cells are systems that have interactions between electrical energy and chemical reactions. We're going to look at two major categories of electrochemical cells. The first one, convert chemical energy using spontaneous chemical reactions into electricity, the movement of electrons. Three different kinds of these chemical to electrical spontaneous cells. We're going to look at primary. These are not rechargeable. Secondary are rechargeable. And then fuel cells. These primary electrochemical cells were first investigated by these two guys, Galvani and Volta. Galvani was dissecting frog legs and accidentally touched the frog leg with two different metal electrodes. I don't know how you accidentally touch a frog leg with two different metal electrodes, but apparently that's the story. And he noticed that the frog leg twitched, and he was like, aha, electricity. And then Volta was like, I don't think we need frog legs to make that happen. And he built the very first battery. So sometimes we call these primary, not rechargeable cells, voltaic cells in honor of Volta, and sometimes we call them galvanic cells in honor of Galvani, but these are all the same things. So a primary cell is the same thing as a voltaic cell, is the same thing as a galvanic cell. Three names, one thing. The second category of electrochemical cells are electrolytic cells. These are flipped. So now we're going to take some electricity to force chemical reactions to happen. Those chemical reactions are not spontaneous. The electricity forces them to happen. Everything that happens in our electrochemical cells relies on redox reactions. We're going to take just a quick moment to review what does that even mean. So reduction, this can be the gaining of electrons and or protons. It can also be a decline in oxidation state, whereas oxidation is a losing of electrons and or protons. It is a rise in oxidation state because it got less negative, which is positive. This reaction, solid zinc turning into a zinc ion and two electrons, this is oxidation or reduction. It is oxidation because this zinc lost those electrons. How about this copper ion? Gaining those two electrons that were lost by zinc. A gaining of electrons is reduction. This copper ion was reduced to copper metal. Those reactions are exactly what drives this primary cell, which we can also call a galvanic cell or a voltaic cell. Here is our oxidation of zinc. We've got our solid zinc. It's losing electrons. Over here, we have the reduction of copper. We've got those copper ions that are gaining electrons being reduced to copper metal. The source of our zinc is this electrode, this big piece of zinc metal that is submerged in this solution of zinc nitrate. What happens is the zinc is going to lose electrons. These zinc atoms are going to release their valence electrons. The electrons are going to flow through that wire. When the zinc atom loses its electrons, it's now an ion. Ions are often quite soluble in water. And so this zinc atom, which is now a zinc ion, is going to be released out into this solution. So now we have made our zinc ions. Those zinc ions are floating around in this solution of zinc nitrate. Those electrons are going to move across all of these wires. Perhaps we add a voltmeter so we can measure just how many electrons are flowing. And then those electrons are going to end up eventually at this piece of copper metal. Because this piece of copper metal is now electrically charged, it's full of electrons, it's negative, it's going to attract these positive copper ions. Those copper ions are going to be attracted to those electrons. The copper is going to gain those electrons and become copper metal. Super cool thing about copper metal, it's not soluble the way that copper ions are. And so this copper ion, when it gets those electrons, is going to be deposited upon this piece of copper. Super cool, right? But this is not the whole story. We also need to replace ions. If I am adding more zinc into this solution, I have more zinc and it's positively charged and more cations and more cations. Now I have shifted equilibrium. I've got all these positively charged things. This is not going to be spontaneous. It's not stable. My reaction is going to stop. So we add the super cool salt bridge, and in the salt bridge we have some kind of solution. This one happens to be sodium nitrate. The nitrate anions are negatively charged. They're going to be attracted to those positively charged zinc ions, and they're going to get added to this solution to keep a balance between the positive zinc cations. We're going to add those negatively charged nitrate anions. On the other side, I'm losing these copper ions because they are being deposited as atoms onto the cathode. That means that I'm going to have a bunch of nitrate and not enough positively charged cations. And so the positively charged sodium in our salt bridge is going to move into this solution, again, to balance out the charges. For every one copper 2+ that we lose, 2 sodiums are going to come into the solution to replace it, keep a beautiful balance of those charges. Sometimes we can shortcut the diagram and show this. This is called a cell diagram. And here we have what's happening at the anode, our oxidation reaction. We've got our zinc solid turning into zinc ion. We're going to draw 2 vertical lines to show the reduction side, where we have our copper ions being reduced to solid copper metal. We have 2 half cells. This is a half cell. This is our other half cell. One half cell has the anode. What always happens at the anode is oxidation. Oxidation always happens at the anode. At our cathode, in this half cell, we have reduction. How I remember cathode is reduction and oxidation is anode is CROA. CROA. Remember CROA. Cathode is reduction and oxidation happens at the anode. Cathode, reduction, oxidation, anode. IB might ask us to draw a primary cell. It's given us 2 electrodes. Let's do it. We're going to start with 2 half cells. We're just going to draw some beakers here. I'm going to submerge into one beaker one of the pieces of metal. I'm going to make this one our silver, and then into the other half cell we're going to submerge our other piece of metal. This is aluminum. We're going to combine these 2 guys. Combine, connect is maybe a better word. Connect them with a piece of wire. We also need to add our salt bridge, right? So we're going to add a salt bridge like this. Perfect. We need to add some solution. So I'm going to submerge my silver into silver. Let's pick nitrate. So we'll have silver nitrate solution. Ooh, that's an AQ for aqueous. And that means on the other side, we need some aluminum nitrate. Also solution. Super cool. Here's our salt bridge. What should we add to our salt bridge? I think that we should add something nitrate. How about some sodium nitrate? Perfect. Let's annotate to show the movement of electrons and ions. So aluminum is higher up on our activity series than is silver. That means that this guy is more likely to be oxidized, and this guy, silver, is more likely to be reduced. That means that electrons are going to be released by the aluminum and they are going to flow over to the silver. So here are our electrons. When those electrons get here, our silver is going to gain those electrons. So we're going to go from silver ion to silver metal. Over here, we're going to go from aluminum solid to aluminum ion, and lots of electrons. In our salt bridge, because we're losing positively charged ions here, our sodium is going to flow that way. We're going to add more sodium ions to balance out the loss of the silver ions. On the other side, our nitrates are going to flow here because I'm adding more aluminum ion to the system, so I need more negatively charged things to balance out all the positive charges of those aluminum ions. Feeling good? Which one is our cathode and which one is our anode? Remember CROA. Cathode is reduction and oxidation is the anode. That means that because silver is reduced, silver is the cathode. And because aluminum is being oxidized, aluminum is our anode. Batteries are simply electrochemical cells. So here's one of the first ones that was built, and it is so super cool. Here you can see our zinc, just like here we have some zinc, and here's our copper, just like here is our copper. In between the zinc and the copper was a porous pot. It acted like the salt bridge. Here we had some sulfate, some copper, and some zinc in between. And so what could happen is that the electrons would flow away from the zinc through whatever circuit we connected our battery to, and then back to the copper. The zinc was still being oxidized. The copper was being reduced. Remember CROA, because the zinc was being oxidized. This piece of zinc is the anode, just like this piece of zinc is the anode. And then our copper is being reduced. It's gaining the electrons that were lost by the zinc that flowed through the circuit. Go back to copper. Copper is our cathode because it's being reduced. Here's another look at a battery. This one is zinc and carbon. Zinc is still being oxidized. This is going to be our anode. Electrons are going to flow away from the zinc through our circuit, whatever it is that we attached our battery to. And those electrons are going to flow back into, here is going to be our cathode. This piece of carbon is being reduced. In between, we have that super cool porous material. This is acting as our salt bridge. And this is a battery. It is a pretty cool electrochemical cell. Some of our batteries, our electrochemical cells, are built to be recharged. We call those secondary cells instead of primary cells. When they are being discharged, when we are using whatever device our battery is attached to, like our phone, what happens is normal old electrochemical movement. So we've got our anode. Our anode is being oxidized because remember CROA, oxidation happens at the anode. So these electrons are being lost from the anode. Our anode is often some kind of graphite lattice that has some lithium atoms embedded in it. The lithium is going to lose some electrons. Those electrons are going to flow through our phone to make our phone work over to the cathode part of the battery. Here, we're often going to have some kind of lithium cobalt oxide complex that's going to gain those electrons until all of the lithium has lost all the electrons and our battery is dead. And then we recharge it. When we recharge, we are going to take some kind of power source. This does not happen without electricity. We need to add some kind of force to make this happen. We're going to add a power source, and it is going to push electrons back over to the anode. That means that, oh my gosh, now our anode is being reduced. Crazy sauce. We are going to add electrons to the anode, which is weird, and it's not going to happen spontaneously. We have to add a power source to force it to happen. As those electrons are getting pushed over to the anode, we're going to steal those extra electrons that the cathode got so that we can send them over to the anode. And this is how we recharge our batteries, is by stealing electrons that just got to the cathode, pushing them back over to the anode. And then our phone is charged and we don't have to have the charger anymore. And then what happens? Those electrons can flow right back over to the cathode when we're using our phone. Often we're going to use some kind of polymer separator instead of a salt bridge because lithium, and lithium is so good for our batteries, lithium reacts quite violently, quite energetically with water. So we definitely don't want any water in our lithium batteries. We're going to use some kind of not water-based polymer instead. Fuel cells are super similar to the electrochemical cells that we've been looking at, with the exception of we don't have metal electrodes. Now we're going to have some hydrogen gas and some oxygen gas. So we're going to supply hydrogen gas to our fuel cell. At the anode, we have a catalyst that is going to oxidize the hydrogen. So we still have CROA going on. We've got oxidation happening at the anode. The hydrogen gas is going to be oxidized. Those electrons are going to be stolen from the hydrogen atoms. The electrons are going to flow through whatever it is that we're trying to power. Perhaps we have a car. Those electrons are going to flow over to our cathode, where oxygen is being supplied. And here the oxygen gas is going to pick up those electrons and also some hydrogen. And if I've got oxygen and hydrogen and hydrogen and some electrons, we make water. And so water is going to be the exhaust of this fuel cell, because those hydrogen ions that were formed when they were oxidized are going to flow through the electrolyte that's here between the anode and the cathode. Those hydrogen ions end up over here so that the water can be formed when the oxygen is reduced by gaining the electrons at the end of the electron flow, as well as those hydrogen ions. How cool is this? It does require a constant supply of hydrogen gas and oxygen gas, but how delightful that the exhaust from this car is water vapor. And the last of our electrochemical cells is the electrolytic cell. Lytic means to split something. Lysis is splitting. We're going to use electricity to split compounds into their elements. This one is kind of opposite the primary cells that we were looking at the beginning of this lecture. In order to make this happen, we do need electricity. That's our power source, because the reaction that is going to happen, this particular redox reaction, is very non-spontaneous. It is not a reaction that is going to happen all by itself, which is why we have to add this energy in the form of electricity. It's going to feel weird. You're going to be like, wait, what? Sodium was reduced? That doesn't make any sense. It does make sense because we're forcing it to happen with this battery. This battery is going to push electrons over here. We're going to have electrons building up here. Electrons are negatively charged. You know what's going to be attracted to a negatively charged thing? A positively charged thing. And if I have these electrodes submerged in molten sodium chloride, what's going to happen is that those sodium ions that are mobile, because this is a liquid, those sodium ions are going to be attracted to those electrons. And what's going to happen when a sodium ion runs into an electron? They're going to mash together to make sodium metal. The sodium ion is gaining electrons. Gaining electrons is reduction. Remember CROA? In CROA, the cathode is where reduction is happening. Here, our sodium is being reduced. This is our cathode. This battery is pulling electrons away from this side. Electrons are being stolen. Because the electrons are moving away, it's losing that negative piece. What's left is positive. You know it's going to be attracted to this positive electrode? Negatively charged chloride ions. You know what's going to happen when that chloride ion gets too close to this electrode where the battery is stealing electrons? The battery is going to steal the electron of the chloride. And so our chloride is going to lose its electron and turn into chlorine. Ooh, that shouldn't be an arrow. That should be a plus. Sorry. And then what's going to happen is chlorine by itself isn't happy. It's diatomic. So it's going to find another chlorine atom and turn into chlorine gas. We're going to have 2 electrons for those 2 chloride ions to make that one diatomic molecule of chlorine. Notice that chloride is losing electrons. Losing electrons is oxidation. This halogen was oxidized. Crazy sauce. That shouldn't happen. Halogens usually gain electrons, not lose them, except that we added that battery to force this reaction to happen. It's a little bit counterintuitive. It happens only because we force it to happen. Because our chloride was losing electrons, and we know that CROA, our anode, is oxidation. So over here, we have our anode, because this is where oxidation is occurring. And on that note, my friends, we have finished this video lecture on electrochemical cells. Hopefully you're feeling pretty confident about the guiding question, what happens when electrons are transferred. All kinds of super cool things happen, right? Our objectives, we defined those electrochemical cells, these interactions between electricity and chemical reactions. We talked about the functions of structures of primary cells. We had those half cells. We had our salt bridge. We had a wire. We talked about recharging, where we use some kind of source to force electrons to go backwards through the cell. We also do that in electrolytic cells, and we use the energy here to split some kind of compound into its elements. Great work today.